Hello students, welcome to the EPG Pathshala. I am Ashok Goyal from the Department of Physics and Astrophysics, University of Delhi. Today we are going to talk on the module named Constraints and Generalized Coordinates from the paper Classical Mechanics. After completing this module, you should be able to learn to classify various kinds of constraints. You should be able to use the generalized coordinates to simplify the description of a dynamical system, and then finally learn to use constraints to identify degrees of freedom needed to specify a dynamical system. Classical mechanics deals with the description of dynamical system, which evolves in a three-dimensional Euclidean space. And you know that in the Newtonian mechanics, the space and time are considered absolute and immutable entities, unlike in the theory of relativity, where again space and time are in fact absolute and immutable, but in special relativity, space and time are integrated into a four-dimensional space-time, as opposed to the Newtonian worldview, which considered space as a separate entity and time as a separate entity. In the Newtonian worldview, motion is described by Newton's laws of motion, and these laws are valid in an inertial frame of reference. The meaning of inertial frame of reference is that any frame which is moving with respect to any other frame with a uniform velocity is called an inertial frame of reference. The dynamical system which we consider, it may be a point particle, a rigid body, or a collection of particles. Classical mechanics was developed by Newton. Now, an alternative and attractive formulation was developed in the 19th century and the late 18th century by people like Lagrange, Euler, Hamilton, Poisson, Jacobi, and others. This formulation does not give anything new, but it imparts a deeper understanding of mechanics. And this alternative formulation made the transition from classical mechanics to quantum mechanics easier, and it has found important role in the theory of classical and quantum fields. Now, what are constraints? See, in real physical situation, the motion is often constrained to move in such a way that some of its coordinates or velocity components satisfy certain relations all through its motion. That is, in physical situation, motion is not always free. You don't have a particle moving freely in a three-dimensional space. You have restrictions. This relation can be expressed, these restrictions, in the form of equations or in equalities. For example, if the motion of a particle is confined on a circle or an ellipse in the xy plane, then the coordinates must satisfy the condition that x square plus y square is equal to a square if the particle is moving on a circle of radius a. If it is moving on an ellipse of semi-major axis a and semi-minor axis b, then these coordinates x and y must satisfy the equation of the ellipse, namely x square by a square plus y square by b square is equal to 1. There are also situations where the particle is confined to move, let us say, within a sphere of radius a. It is not, it's like a gas which is confined in a spherical cavity of certain volume. Then in that case, the coordinates of the particle have to satisfy the constraint that x square plus y square plus z square is less than a square, where is the radius of the cavity. Now, the constrained motion results on account of it results in certain forces. which are called constraining forces. Why is it so? Now, just imagine a block moving on a plane surface like on a table. If I put the block of wood on a table and don't apply any force, it is at rest. Why is it at rest? Even though this block of force experiences a gravitational force pulling it downwards. But because of the fact that motion is constrained on the top of the table, the surface of the table provides a constraining force which is generally normal to the surface, and it counters the force of gravity such that the normal force exactly equals the force of gravitation and the block remains at rest. Now if I apply a force on this block, the force the block is free to move on the surface of the table, but it cannot move out of the table. Therefore, the normal force is always acting against the force of gravity to keep it on the table. So the constraining motion results in certain forces called the constraining forces, which arise when the particle is in contact with the surface or the curve on which it is constrained to move, and normally this constraint force is normal to the surface. Constraints can be classified in different classes depending on their nature. Constraints are, for example, called holonomic constraints if they can be expressed in terms of algebraic equations, like in the case of a particle moving on a circle or in an ellipse. So if r1, r2, etc. are the coordinates vectors of a particle, if there is a relationship between these various coordinates, some function f r1, r2, t equal to 0, then is a holonomic constraint. They can also be made independent of velocities. If the constraints depend on velocities, that is, holonomic constraints are expressed in terms of algebraic equations and they are independent of velocities. If the constraints depend on velocities and if they cannot be expressed in terms of either algebraic equations or integrable differential equations, then in that case, the constraints are termed non-holonomic. Now, non-holonomic constraints may involve frictional forces, or they may be expressed in terms of an inequality like x square plus y square plus z square is less than a square, or in terms of differential equations which are non-integrable, like for example the equation x dy minus y dx is equal to cx square. The constraints that do not depend on time explicitly, they are called cylindronomic, and if the constraint depend on time explicitly, they are called vinomic. Further, the constraints are said to be conservative if the total mechanical energy during the motion is conserved, and the constraints are called dissipative when the constraint forces do work and the mechanical energy is not conserved. We have classified constraints as holonomic and non-holonomic, and also constraints which explicitly depend on time and those which do not depend on time, and constraints which involve velocity or do not involve velocity. With the help of certain examples now, we will illustrate these different classes of constraints. Let us assume that a particle is confined to move on the surface of a sphere of radius a. Then the Cartesian coordinates of the particle would satisfy a constraint equation x square plus y square plus z square is equal to a square. Therefore, this constraint is given in terms of algebraic equation, and therefore the constraint is holonomic. As a further example, let us consider the motion of an atom which is constrained to move in a rectangular cavity whose length is L, breadth is B, and the width is W, such that its Cartesian coordinate x lies between A and L minus A, the coordinate y lies between B minus A, and z lies between A and W minus A. In view of the fact that the coordinates of a constraint system satisfy certain relations, the number of independent variables required to fix the position and configuration of a dynamical system is reduced because of the constraints. The constraints satisfy certain algebraic equations or certain differential equations which are integrable. Therefore, the number of independent coordinates required to fix the position and configuration of a dynamical system is correspondingly reduced. The number of independent variables which are required for the description of a constraint system would be designated as U1, U2, Un, and these independent variables which are required for the description of a constraint system are called the number of degrees of freedom of the system. And obviously, if a particle is undergoing a constrained motion, the degrees of freedom of the system is less than the number of coordinates required to fix the position of each particle in the system. Now let us, with the help of some examples, see what we mean. Assume a free particle moving in three-dimensional Euclidean space. We know that a particle free to move in a three-dimensional Euclidean space has 3 degrees of freedom, x, y, z, in the Cartesian coordinates, and each of these coordinates can vary from minus infinity to infinity. Therefore, a free particle has 3 degrees of freedom. Now, if we have a system, dynamical system consisting of n free particles, then its number of degrees of freedom is obviously 3n. Now, consider a diatomic molecule having 2 identical atoms which are joined together by electromagnetic forces such that the bond length remains fixed. So, how many degrees of freedom does it have? There are 2 atoms. If they were free, each atom having 3 degrees of freedom, total number of degrees would have been 6. But since the atoms are tied to each other by electromagnetic forces which do not change, therefore the total number of degrees of freedom is reduced. It becomes 3 into 2 minus 1 is equal to 5. So this diatomic molecule has then 5 degrees of freedom. Now let us take the example of a rigid body. Now what is a rigid body? A rigid body is a mathematically idealized system with a large number of particles with fixed distances among all the particles. Now, first thing you notice is that a rigid body is an ideal conception, and in practice it does not exist. And in fact, according to the theory of relativity also, a rigid body cannot exist, because a rigid body means that the configuration of the molecules or atoms inside it remains fixed. But we know that if we disturb the configuration at one point, it will be transmitted by a velocity which cannot be greater than the velocity of light, and it will take a finite time to reach out the other end of the rigid body, such that the distance between all the parts of the rigid body remain fixed, which is not possible by special theory of relativity. But we will continue to use this as an idealized concept, just as a particle is used in mechanics as an idealized concept and is assumed to have no size. So, how many coordinates are required to fix the orientation and position of a rigid body? Now, see that if you fix 3 points in a rigid body, which are not coplanar, but we know that any 3 points in space constitute a plane. So, and since the distance between these points remain fixed, so the fixing of these 3 non-collinear points would fix the orientation and position of the rigid body. And therefore, to fix that, we require 3 into 2 is equal to 6 degrees of freedom. And once these three arbitrary points in the rigid body are fixed, the rigid body is completely fixed. So it's important to remember that a rigid body has 6 degrees of freedom, and normally this 6 degrees of freedom are chosen as 3 coordinates of the center of mass and 3 angles to fix the orientation of the body, and these 3 angles are normally taken to be what are called Eulerian angles, which we'll discuss later. Now, to see how the use of degrees of freedom, which is reduced because of the constrained forces or the constraining motion, makes the description of a physical phenomena or a dynamical system simpler. As a very simple example, which you have already studied in the school, assume a block sliding without friction on an inclined plane. The block is sliding on an inclined plane. The angle of the inclined plane is, let us say, theta. So if we choose our coordinate axis in such a manner that x lies along the inclined plane and y is perpendicular to the inclined plane, since the motion is constrained along the plane, so only it has 1 degree of freedom, that is x. So we can say the coordinates, choose the coordinate system such that x-axis is pointing along the surface of the plane and the y-axis is normal to the plane. The block is confined to slide without friction along the plane. Therefore, the constraint is that there is no motion in a direction perpendicular to the plane, so y remains constant, and therefore the equation of motion can be simply written as, from the Newton's equation of motion, that mass into acceleration is equal to force. So mx double dot, which is mass into acceleration, is the force along the direction x, that is along the plane. And what is the force acting? The only force acting is the gravitational force mg, which makes an angle theta with the normal to the plane. Therefore, the component of this force along the plane is mj sine theta, and therefore the equation of motion is mx double dot is equal to mj sine theta. Since there is no motion along the y direction, so we have my double dash must be equal to 0 because there is no motion along the direction of y, and it is here that the constraint forces come into play. So my double dot is equal to the constraint force n, which is called the normal force, minus the gravitational force perpendicular to the plane, which is along the direction of y, which is mg cos theta. So the equation of motion along the y direction is my double dash is equal to n minus mg cos theta is equal to 0. And since there is no motion along the y direction, that means the constraint force must act normal to the plane, and its magnitude is given by n is equal to mg cos theta. We can easily integrate this equation. We can easily integrate this equation to obtain the acceleration. So we have x double prime is equal to g sine theta. Integrating, we get x dot is equal to x dot at time t is equal to 0 plus g sine theta t. Integrating once again, we have xt is equal to x of 0, that is the position at time t is equal to 0, plus integral of the velocity at time 0 plus g sine theta into dt. So we get that x of t, that is the position of the particle along the block at any time t, is equal to the position from initial position plus the initial velocity time t plus half gt square into sine theta. If the particle starts or the block starts from rest, we have the initial position and initial velocity is equal to 0, and in that case the position at any time t of the block is given by xt is equal to half gt square sine theta. As a second example, we take the well-known example of Atwoods machine. What is Atwoods machine? In Atwoods machine, two masses are connected by a massless inextensible string of fixed length passing over a frictionless pulley, and the two masses which are attached to two ends of the string. Let's call them M1 and M2. Now, first thing is to note that this system has only 1 degree of freedom, because if we choose the coordinate systems as shown, that the x-axis is horizontal passing through the center of the pulley, and y-axis are chosen to be perpendicular to x and pointing downwards. And then, since the length of the string is fixed, so position of the particle M1 is given by the coordinate y1, and position of the particle M2 is given by the position y2, but we have y1 plus y2 is equal to L, the length of the string. Therefore, of the two coordinates y1 and y2 required to fix the position of M1 and M2 at any given time, there is only one independent coordinate, because y1 plus y2 is equal to length of the string. Now, let's assume that T is the tension in the string, and since the string is inextensible and therefore the tension is opposite to the force which is acting. The force acting on the mass M1 is the force of gravity M1g downwards. Force acting on the mass M2 is likewise the force of gravity acting downwards. The tension in the two segments of the string is upwards, and in both the string the tension is equal, because if the tension is not equal, then in that case the string will have a motion. A string is massless, it's not assumed to have any motion, is inextensible. Therefore, we can write the equation of motion for the mass M1 to be M1 y1 double dot, that is acceleration of the mass M1 d2 y1 by dt square, is equal to force acting on it. Force acting on it is a downward force minus M1g plus the tension upwards. Likewise, the equation of motion for the mass M2 is M2 y double dot is equal to minus M2g plus the tension which is acting upwards. As we mentioned earlier, since the length of the string is fixed, so y1 plus y2, because y1 is negative, is pointing downwards, so y1 plus y2 is equal to minus L. Therefore, y2 is equal to minus L minus y1. So y1 dot is equal to minus y2 dot, because the string length remains fixed, and therefore the acceleration of y1 is equal to minus the acceleration of y2. If the mass m1 goes down, the mass m2 goes up. Therefore, the equations become m1 y1 double dot is equal to minus m1g plus m2 y2 double dot plus g, and therefore m1 plus m2 y1 double dot is equal to m2 minus m1 into g. Therefore, y1 double dot is equal to m minus of m1 minus m2 divided by m1 plus m2 into g, and we can use this to substitute in any of the equations to obtain the tension, and the tension is given by 2m1 m2 divided by m1 plus m2. Let us now talk of generalized coordinates. We have already seen that for a system of n particles, if there are k independent constraint equations, the number of degrees of freedom is 3n minus k, because each particle in Euclidean three-dimensional space has 3 degrees of freedom. So n particles have 3n degrees of freedom, and k are independent constraint equations which relate these coordinates. So the number of degrees of freedom is 3n minus k. So what does it mean? It means the dynamical behavior of the system depends only on the coordinates corresponding to the degrees of freedom. Since there are fewer degrees of freedom than the position coordinates required to specify the position of each particle in the system, can we eliminate the unnecessary coordinates? So this is the question. Because the number of coordinates to fix the position of the system is more than the degrees of freedom of the system. This will undoubtedly simplify the analysis of the motion, particularly if we choose coordinates that take into account the constraints, and if these coordinates are so chosen that they are independent, such coordinates we call generalized coordinates. Now, if the constraint is holonomic, then it is indeed possible to define a set of 3 minus k independent coordinates called generalized coordinates, represented as the set of coordinates qk. K is the subscript which varies from 1 to 3 and minus k, that specify the motion of the system subject to the given constraints and which are independent of each other. That is q1, q2, qn, etc. If n is the number of degrees of freedom, then we have generalized coordinates q1, q2, qn, and by qk we represent the set of the generalized coordinates q1, q2, qn. Then for the holonomic system, it's indeed possible to write down the Cartesian coordinates r1, r2, etc. The Cartesian coordinates required are 3n times the number of particles in the system. So the Cartesian coordinates can be expressed in terms of generalized coordinates q1, q2, qn in terms of the known functions, and this is possible for holonomic constraints. Therefore, the position coordinate of the ith particle Ri can be written as a function of the generalized coordinates q1, q2, qn and time also if they depend explicitly on time. So Ri is the position vector, so it can be written in terms of components. Each Ri has 3 components, say x1i, x2i and x3i. So in terms of components, it means that each component required to fix the position coordinate of the system of particles can be expressed in terms of known function in terms of generalized coordinates q1, q2, etc. That means x1 can be written as some function of q1, q2, qn and t, x2 as some other function x2 of q1, q2, qn, and since for a system of n particles there are 3n components required, so x3n can be written as some other function x3n of the same generalized coordinates q1, q2, qn and t, where obviously the number of degrees of freedom n is equal to 3n minus k. It may or may not be always possible to have an analytical expression for these functions, but in general we can write each of them in terms of the generalized coordinates. The beauty of the generalized coordinates is that they eliminate the constraint forces from the problem, and the generalized coordinates that are independent. The generalized coordinates, of course, need not be the Cartesian coordinates. They can be chosen according to the problem considered. For example, if you're considering the motion of a particle on an ellipse, x square by a square plus y square by b square is equal to 1, then we know because the particle is confined to move on the ellipse, it has only 1 degree of freedom, and therefore we can choose one polar angle theta. Then the particle coordinates x and y can be expressed in terms of the generalized coordinates theta, as x is equal to a cos theta and y is equal to b sin theta. The generalized coordinates eliminate the constraints, forces from the problem, and they are independent. They need not be Cartesian, can be chosen suitably as I mentioned before. In the case of a particle moving in the ellipse, for example, we can choose them to be x is equal to a cos theta. We can express the Cartesian coordinates x and y in terms of generalized coordinate which is theta. And chosen in this way as x is equal to a cos theta and y is equal to b sin theta, constraint equation is automatically satisfied. Just as the velocity components for Cartesian coordinates are given as vi is equal to the time derivative. Remember, this is a total time derivative. Vi is d dt of xi. That is, That is, if I represent my system by Cartesian coordinate x1, x2, etc., then the corresponding velocity components are obtained by taking the total time derivative of the coordinates. So in the same vein, we define generalized velocities as the total time derivative of the generalized coordinates, namely the generalized velocity qk dot corresponding to the generalized velocity qk is obtained by taking the total time derivative of qk. You know, the velocity is defined as a total derivative of the Cartesian coordinate in the Euclidean space. Now, in terms of generalized coordinates, we define velocities again in terms of total derivatives of the said coordinates. Let a function f of the generalized coordinates qk, and it may also depend explicitly on time, then the total derivative of this function is given in terms of the chain rule, because this is a function of a set of independent generalized coordinates q1, q2, qn, etc. And each of them depends on time. Therefore, by the chain rule of differential of a function of several variables, then d dt, that is a total derivative of the function of a set of generalized coordinates qkt, can be written as a sum over k partial derivative of the function f with respect to this particular generalized coordinates qk into the total derivative of qk with respect to time, sum over all generalized coordinates k, plus the partial derivative of f with respect to t. So the use of generalized coordinates in place of position coordinates of the system, if you remember, was to eliminate the non-dynamical degrees of freedom from the system. Now, in a similar manner, constraint forces can also be eliminated, leaving only the generalized forces. So we have constraint forces, and you remember the constraint forces do not appear anywhere in the dynamical description of the system. So let us start with the forces which are acting on each particle. So consider a force Fi, which is a function of the position of the ith particle, with the force acting on the ith particle of the n particle system. That is, Fi Ri is the force acting on the ith particle. Now suppose this ith particle makes a small arbitrary displacement delta Ri. Remember, this R is a vector. Let us represent the vectors. So the work done by the force for an arbitrary displacement delta Ri, you remember, is force into distance. So the work done by the force Fi acting on the ith particle when the ith particle position is displaced by an infinitesimal amount delta Ri is Fi dot delta Ri. So therefore the total work done by the system of all the forces acting on all the particles, if represented by delta W, the delta W is the sum over I of the work done on each particle I, which is Fi dot delta Ri. Now, we have seen that the position vectors Ri's can be expressible or can be expressed in terms of generalized coordinates as Ri being a function of the generalized coordinates q1, q2, qn. Therefore, delta Ri, again by the chain rule, is sigma over j, partial derivative of Ri with respect to qj into delta qj. Substituting in the expression for the total work done, that equation 1.17, then delta W can be written as sigma over I from 1 to n, Fi Ri dot delta Ri, delta Ri substituted from 1.19, which is the sum over j from 1 to r, delta Ri by delta qj, which can be written as by interchanging the integral, the summations as delta qj sum over j into a sum over I fi, a function of ri dot dri by dqj. Now, if you just remember that the work done delta w is fi dot delta ri, and here we express it in terms of some quantity in delta qj. So that quantity which multiplies the delta qj is some kind of generalized force. So we can define a generalized force F acting on jth generalized coordinates as the sum of the vector Fi, that is the force acting on the ith particle, dotted with the variation of the ith particle position with respect to the jth generalized coordinates. So we define the generalized force Fj acting on the jth generalized coordinates as sigma over I fi ri dot dri by dqj. And then the total work done on the system can be written in terms of only the generalized forces and not in terms of the applied forces on all the particles. So delta W can then be written in terms of the script Fj, that is generalized force, dot delta Qj sum over j. Thus we can express the total work done in terms of generalized coordinates and forces. The expression sigma j Fj dot delta Qj denotes the work done by all the generalized forces which equal to the number of degrees of freedom of the system in the arbitrary displacement in generalized coordinates. Now remember that Fj is the component, so it's not a vector. Fj is the force component on the jth generalized coordinate. So we are able to then write the work done in terms of the forces on generalized coordinates. Let's go back to the example of Atwood machine to see what we mean. Now choose the coordinates as shown earlier. So y1 and y2 are the positions of the masses m1 and m2 from the horizontal plane passing through the pulley. The y-axis points upwards since the length of this thing is fixed and doesn't change. So L is equal to minus y1 minus y2. Let us choose y1 is equal to y as the generalized coordinates. Then the generalized velocity is given by y dot is the total time derivative of y with respect to t, which is again dy1 by dt is equal to minus dy2 by dt. That velocity y dot is equal to the velocity of the particle m1 and is also equal to the velocity of minus the velocity of the particle 2. The force F1 and F2 then acting on the masses m1 and m2 are, we can see F1 is equal to a force acting downwards, which is m1 gy1, force acting t plus t upwards. So F1 is equal to minus m1 gy1 plus t multiplied by the unit vector along the y direction, which is equal to m1 gy, because y1 plus t into y, because we have chosen y as a generalized coordinates equal to y1. So f1 is equal to minus m1 gy plus t and is along direction of y, and f2 is equal to minus m2 gy2 plus t along the direction y, which is given as minus m2g minus l minus y plus dy. So generalized forces then can be all the f1 and f2. They are the forces f1 and f2 acting on them. So as an example, we are considering this famous Atwood machine, which you're all familiar with from your school days. The Atwood machine consists of a string of a fixed length L passing through a frictionless pulley. The pulley is fixed at some point in the horizontal plane, and the string is inextensible, massless. It has a length L, and at the two ends of the string are two masses M1 and M2 attached, and the string passes through the pulley. Now to analyze this motion, now set up the coordinates as shown. Set up the x coordinate horizontal and y coordinates upwards positive. In that case, at any given point in time, the position of the mass m1 is given by the coordinate y1 and that of m2 is given by y2. And remember that y1 and y2 are in the negative y directions. And since the length of the string is fixed, so y1 plus y2 is equal to minus L. So now the work done, total work done delta W is F1 dot delta Y1 Y cap, Y hat is unit vector along the direction of Y, plus F2 dot delta Y and Y hat. Now delta Y1 is equal to delta Y and delta Y2 is equal to minus delta Y. Therefore, the work done is F1 minus F2 delta Y along the direction Y, which can be written as minus G M1 minus M2 delta Y. Therefore, the generalized force we can see is along the direction Y, and the generalized force is minus G into M1 minus M2. So just see, the force on each masses M1 and M2 is M1G and M2G respectively, both downwards, but in terms of the generalized coordinate Y, which is Y is equal to Y1, and since Y2 is related to Y1, so Y2 can be written in terms of Y, and then the generalized force simply becomes as minus G times M1 minus M2. So, students, let us summarize what we have learned in this module. We have learned that the constraints, which can be expressed as algebraic equations or in the form of integrable differential equations, are called holonomic. And further, if a holonomic constraint depends on time explicitly, then it is called vinomic. If there is no explicit time dependence, then these holonomic constraints are called cylindronomic. Non-holonomic constraints involve frictional forces, or else they are expressed in forms of inequalities. And the number of independent variables required for the description of a system is called the number of degrees of freedom. And for example, if you have a free particle moving in a Cartesian in Euclidean space in 3 dimensions, it has 3 degrees of freedom. And if you have n particles, you have 3n degrees of freedom. And as we have seen during the course of this lecture, that a rigid body has 6 degrees of freedom. Thank you.